presentation mode. Okay, so I don't know, do you see it? Everybody see it? I see it here, so supposedly everybody would see it. Yeah. Well, I'm JAMIL ABDO, Dr. JAMIL ABDO. I would like first to thank you all for the invitation, I'll just here talk about like the autonomous vehicle LiDAR sensor assessment. In general, I'll talk about a general topic first about the autonomous vehicle, then I'll talk about the work that we've done that is related to LiDAR sensor, and we assess LiDAR sensors, or at least two LiDAR sensors that is the most popular here in the US. So let me also acknowledge my colleagues, Spencer Hamblin. He's an electrical engineer. He's in the Frostburg State University, and Genshin. He is the CEO of the Intelligent Fusion Technology. That is the let's say the company that is sponsored or funded the project or part of the project. Mainly, this project is funded by the state through the Maryland State Partnership, which is the what do we call it, MIPS. It is like part of the state that is sponsored projects here, mainly high-tech projects, and they require like the companies to let's say sponsor part of it, goes from 25 or 20% to 50% based on the company size. So as I said, I will first I'll go into the introduction of like autonomous vehicle or autonomous driving, let's say, and maybe we know now that these cars are really hitting the roads, and by like 2022, there will be like about 11 million, let's say, vehicle that would be hitting the road, meaning driving on the roads, and we call them like autonomous vehicles. But in general, let's say those are would be in a different level. Some of them would be a little advanced, some of them would be less advanced. When we say vehicles means that it is not just only cars. There would be like trucks, there would be mainly, you know, those mailbox trucks or vans that they use to deliver the let's say the mail. Those are part of the autonomous vehicle or AVs. In 10 years, things would be different. We know that the AVs will be the norm, meaning that many of the cars would be, or the vehicles in general would be like autonomous, kind of autonomous, or we don't want to say, because there is like a level on next page that would be showing that there is like a level goes from 0 to 5 or from 1 to 5. So with the certain level. So that would be one. And the other thing is like here, one of the advantage of like using the autonomous vehicle in addition to like self-driving is let's say 90% of the let's say the accident would be reduced, or like we have 90% of reduction in vehicle let's say crashes. That's one of the major things that we would say would be beneficial of using the vehicle, let's say, or AVs. Next page, please. So this is what I was talking about. This is like the SAE, the level of automation, and that goes from 1 to 5. You can say like 0, there is no automation at all. And in 1, there's like a driver assistant, which is like here is like the vehicle is controlled by the drivers, but some driving assistance features may be included in the vehicle design. So that is, you can think of the current vehicles, actually they do have this. I mean, if you have a newer car now, you would see kind of assistant, meaning that the cameras, meaning all of these things that you would see, front camera, back camera, GPS, all of that would be there. And it goes all the way to, let's say, full automation, which is the vehicle is capable of, let's say, performing all driving functions under all conditions, meaning that you just sit in the car. Either you just say, okay, well, I want to go to that place, and then the car would do everything. You don't have to do anything. But we are not on that level yet. It is like, it's a long way to reach that. Actually, the vehicles or autonomous vehicles now operating between like level 2 and 3, mainly tilted towards, let's say, level 3, which is conditional automation, meaning that the driver is necessary in the car, but it is not required to monitor the environment. The driver must be ready to react. That is, as I said, it's not there, but under certain conditions, meaning that if we go to certain locations in, let's say, here in the US, I'm talking about US here, there would be like kind of those cars, you'll see them there. Driver is sitting here, he's watching for anything, then they will interrupt. And those mainly in places where they have clear skies and I mean, let's say we can say ideal conditions or certain conditions. So this is why we can say we are in between, let's say, level 2 and 3. Next page, please. Okay. So to continue, like introducing the topic of, let's say, AVs, these are the basic physical ecosystem of the autonomous vehicles. It's just like you will see that this is a car. I don't know if you've seen this. On the top of that, there's like, that's what we call it, the LiDAR, or the light detection and ranging sensor. That is the one that we're talking about here. And there are other sensors, and you have like a camera here, and you have like yes, yeah. There's like a camera, ultrasonic sensors, central, let's say, computers, and you'll see here also the radar sensors, and you'll see like excuse me, can you hear me? Can you hear me?
Yes, go ahead, Dr. JAMIL. Listening.
Yeah. So it is, yeah. So it is all of these components, let's say, sensors and all of that would be in the car, and mainly here the focus on the LiDAR sensor. Let me just say this: like, not all the cars. Can you go to the following page, please? Well, not all the cars that they would use the LiDAR sensors in the future. We'll talk about like a LiDAR sensor in a little bit, but let's say Tesla here in one of the major companies for let's say in the US, which is like using the or going heavily into the autonomous or AV side, which is and it's in the market. They're not using the LiDAR. They are using the cameras in general, the cameras. And they would saying that if we can see something and we recognize it by seeing it, by driving it, now we go from one place to another using our car, then we can make the car just visualize this and process it, and then we would will be able to see the let's say to manage things in general, that they're going onto that side rather than going into using the LiDARs and all of that. But many companies are really using they're using the LiDAR systems. Next page, please. Can you move to next page? Yes, thank you. And just to I mean, this is just to show you that those are really the companies that part of the companies. Maybe it's not the whole list of the companies, major companies that they are using the or they are going into the autonomous vehicle driving in the in the I mean, they're now working on it, and many of them, they are implementing some of the techniques that is used, either LiDAR or camera or any of these. So let's say here is Tesla, Ford, BM, and Audi, and all of that, like Mercedes and Nissan, and all of these big companies. In addition to that, there are like those IT companies like Intel and Microsoft and Google, and all of that. They will see them that they're using that. And you see here, if you look at it, like FedEx is, this is like post delivering, like the mail. So they will use that. They start using this. They implemented this, and they are on a level 2 to 3, as I said. And in the future, things would be like, you'll see a car coming, delivering the mail to your house, or to whatever, to your address, just by itself. So this is the near future. And as we said, we're talking about, like, here, it's not like really 50 or 60 years. We're talking about like 10 years, if it is not less. Next page, please. Yeah. So so now we'll go to the objective of the work that we've done, that is related to autonomous vehicles, but we're focusing here on the let's say the LiDAR system, and the LiDAR system is the sensor that is used to sense things there, and I'll talk about it in a little bit of detail later. But the work that we've done here is we want to test, let's say, the performance of the sensors. And we went here to the main companies in the US, which is like Paladin and Oster, and we use like 2 of these sensors, or their LiDAR sensors, and we want to test them in certain conditions, meaning that extreme conditions, meaning in adverse conditions, heavy rain, heavy snow, and fog. The way it is tested now, it's in the US, it is tested in Texas, California, where it has like perfect like conditions. You can talk about like, let's say, clear skies or sunny days or something like that. So it is not really where it's not the norm where it should be. So why this area? We are here in Maryland, let's say, 2 places. One place, as I said, is like University of Maryland. That is the where we test first, and there is like another place which is close to the Frostburg, which is like a place or a town that has like all let's say heavy conditions that would be shown there on the during the year. So we would have like here heavy rain, heavy snow, and heavy fog. I mean, if I look at it outside now, it's in the summer, but you can see like something up to like 20 meters, 30 meters. Beyond that, you can't. It's very foggy. So it is like those are the extreme conditions, and we would like to study or to understand how the LiDARs would behave within these certain conditions. That is one thing. And this also would be reflected on the way that we do it is just we want to determine the effective, something we call it an effective range, to estimate the maximum range at which the LiDAR sensor can return points. So this is how it works. I mean, this is what we're going to do. And in general, what is LiDAR? LiDAR is like light detecting or detection and ranging. So sometimes it's called laser scanning or 3D scanning. And you see that this is kind of a scanning that you see a car, a vehicle is driving, and then you scan everything around you. So you just, a laser is sent to the, let's say, sent from the LiDAR, and it is getting reflected back from those objects, all objects around you. And then it is a process, and then from there, here you see in that let's say picture, it's just like this is a typical. This is what happens is like the LiDAR send this to the object, and then it is like the LiDAR or the let's say the laser would be reflected back and collected here and processed. So in general, this is the car, typical car. So it's sensor emitted, like the LiDAR sensor emit pulses. And here, these pulses would be reflected back. And then here we have like certain distance, like sensor use the time in general, how we would do that is just like we use the time, the sending the, based on sending the pulses and returning these pulses. So kind of an equation that we would know that there's a difference in actual time. So it would be like in here, this is how we would how the sensor would detect that object and what the size of the object and the obstacles that you would see around the sensor. Thousands and thousands and thousands of like pulses would be sent every second, and would be collected and processed. And in general, we would say that, okay, well, for this, it would be like really, if you are a car or a vehicle that using a LiDAR sensor, it's like having a 2,600 internet users at the same time. So it's a lot of data that is processed. So when you compare to like 2,600 or even more. And we, as we said, we're like repeating this process a million times per second, the creation, and this would create the pictures that I showed you before, which is mapping or 3D mapping of the environment. And then these pulses would be processed, and decision is taken, and then the car would, okay, go further, stop, move left, right, slow down, or do whatever things that it's supposed to do. Next page, please. So yeah, as I said, the main purpose here is we want to make sure that whenever it is, it's not normal, it's not like ideal conditions, then the LiDAR would really react well or not. That is the goal. So we tested the LiDAR under, let's say, heavy snow and rain and fog. As I said, we took two LiDARs, one Validane LiDAR with the 32 channels, and the other one is an Aster with the 32 channels, just to make sure that we're doing those of the most popular, let's say, LiDARs. Validane is mainly the very well known all over the world, and this is a company that started like I think 1983, and they are continuing doing this. They're successful in the market. Well, we just see here that if you, on the left side, you'll see that if we send a signal with let's say 32 channels, then we would receive pulses back by, let's say, those red dots that would be reflected. And if you have like higher channels, let's say, then we would receive more of these. So the number of channels of traditional LiDAR determine the number of independent beams that is transmitted back to the transmitted and received back. So as I said earlier, like we use the effective range to describe the situation in a minimum number of points. So the point is, like, the more channels that we have, the more points that we can get, or it can be reflected and can be read by the controller and all of that and processed. And these channels, like it depends on, like, if you go from 4, 8 to 16, 32, or 64, let's say, channels, then you will be able to get more of these points, and you will be able to cover like a longer range. Let's say if we are talking about here 100 meters, then will be for more channels. We'll talk about like more of these, let's say, more meters. Let's say 150 to 100, depends on the number of channels. So the channels, for sure, it affects number of channels. It affects the data that we collect and the distance that we're talking about, or the effective distance that we're talking about. Next page, please. So what we did is, like, okay, we took here, testing setup. As I said, we said we'll test this in this adverse condition, weather conditions, and we start from 100. We started, I think, with more than that, but then we would say the effective range for 32 channels started at 120, let's say, meters. And then we use those Validine and Aster, and we built, like, first we started by building testing platforms, and you see that all of these, like here, we have the units here, and we have the LiDARs on the top of that. And as I said, in cars, you'll see that the LiDARs are now they place them or install them on the top of the cars. So that is one thing that is now it has been changing, where you have the lidars going into smaller size, and they're going into, they implement them or try to put them inside the car, which is like, I mean, you know, it's just like for safety, for you know, for easier driving and all of that. So so that's the testing platform that that we use. It is portable. It's we take it from one place to another. We chose like different locations, and mainly the location in Frostburg, where we had like an open street that we are not distracted with lots of cars, and then we would do the testing testing there. Can you go to the second page, please? Next page. Thank you. Yeah, those are the testing procedure. As I said, you see that here we the way that we do it. If you look at the picture on the left, in the middle here, we would see that this is the setup that we use, and those are the lidars on the top. We would have like a car that is driving from that street and going into towards the lidar unit here, and we use both of them to collect data at the same time. This is like here, it's just a clear sky. We did like other stuff here with just like in the snow and heavy snow. We did it in a foggy place, and actually some of it is like foggier, but you can't see. I mean, if we put the pictures here, it's not, doesn't make sense. And let's say the car, as I said, it goes and let's say drive from 120 meters or 150 meters, and it goes into like every 5 meters or 5, let's say it goes into let's say every 7.5 meters, it stops, and then we would collect the data for let's say for 10 seconds, and then it moves on and stops at the 7.5 meter, and then it moves on until it reached the lidar unit. That is what we call it static driving, and static way of collecting the data. We've done this in project one that is like started about 2 years back, and we've done from that. And now we started a new one where we have, let's say, data that is that goes into, let's say, that we collect data while the car is driving, meaning that non-stop. Okay, next page, please. So softwares we use like the robot operating system, ROS. That is like the software that is. It's actually to interface with the unit. We use that ROS, let's say, software, and we developed or we wrote our let's say program to analyze the data, and the data, as you've seen here, it would be like here collected in a box, depending on the, as we said here, and the distance that we're talking about here, 100 meters, 50 meters, or whatever, and then you'll see that. The data with how many reflected point within this box would be there, and then it would be counted, and see that based on that we would decide on the effective data, on the effective range of the sensor. So we know exactly how far is that car, and then we compare it to the how the number of points that is collected, which is the effective range. And the data that we get would just go to this. Just present part of the work. Yeah, please go to the next page. Yeah, we've seen that this is this is kind of data that we collect. I mean, it's just like here it is like it shows some of interference during the rain and the snow, but it is like, this is how we do that. This is where is the car and the unit, and this is where we can, those are the red lines, or are those the let's say the we can say those are the channels, and then we collect the data here on this. And what I've seen here on the top is like the results from the Validine and Oster, let's say Oster lidars. You'll see that here for like the blue line here just shows the clear day, and then we'll see that let's say the snow. Well, it didn't show that it is like a big difference between the clear day and snow day, meaning that there is no effect of the snow on the LiDAR. When we compare these things with the rain, we see that there is a little bit of there is an effect of rain, but not very much. But there is an effect of rain, as you see it here. We collected the data, let's say over 4 times, meaning that whatever things that you've seen here is just like it is like rain in 4 days, I mean heavy rain in 4 days. And then we averaged that, and this is the results that you would see. So we are repeating this to make sure that we are collecting, we are like really getting the right thing. And the uncertainty is, we worked on the uncertainty, and we find that it's between like 1.5 to 2.5, let's say, percentage. So we've seen that. The most effective, let's say, condition is shown here is really the fog, and as you see it here in the like red or let's say orange line here, it is once you start like if we are at 200 meter, or if you are at whatever 100 meter or 80, or there is like an effect of that, let's say. The effect of fog, and this is why it was like strange that snow didn't show that, but we repeated that snow that testing many times, and it didn't show that it has like the effect on the performance of the LiDARs. And as you see here, like there are like Validyne and Aster, they gave the same results almost. The only difference is that there's like the threshold points is different, meaning that it depends on the way that it is that sensor is used to measure, like meaning that the angle that they cover. So it is the difference, that is the performance is the same as far as like the influence of the weather conditions, but the coverage, that is the sensor with cover, is different based on the manufacturer themselves. Next page. Thank you. And you would see that this is just like the effective range, and we see that here the point of thresholds, like here we have like 5 points. If we collect that 5 points, meaning that we'd have for a clear day, that's the effective range, almost 100 meters. And then for, as I said, it is like for over 4 days, we've done that. I mean 4 let's say times, meaning that 4 different days. And for the rain, we've got the uncertainty is 1.2, and like for the rain, this is the first one for the clear day. The rain is like 91.8, and all of that depends on the point threshold. And we'll see that the uncertainty of all of them, it's within like within 1 point, let's say 1.20, 1.2 to let's say 2.5, and some of the other results. And as I said, the effective range is like, this is for let's say a comparison between Validyne and Aster. And as I said, they are very comparable. But the difference is the point threshold, which depend on the manufacturer themselves, because the way that they cover the data. And it's the next page we would see the difference between those as far as the manufacturer like point of view, manufacturer objectives. Can you go to the next page? So next page, please. Yeah, so that's what I'm talking about. As you said, like the effect was like the effect of let's say fog was the most critical, meaning that it has the big influence, or the largest influence on the let's say the on the LiDARs. And the difference is like here, because like we said, that like the difference in thresholds for the effective range comes from the way that it is covered. See that here we have like the Validyne covers like from -25 to let's say 15, and that is different than if we are covering if we are looking at the Aster. And so in general, we don't want to present more of these results. but yeah, please go to the conclusion. So in general, what we did is like we're looking at the autonomous vehicle. We know that the autonomous vehicle is the future. Within 10 years, things would be changing. So let's say if you buy a vehicle now, 10 years, it's not going to be, well, at least in some places in the world, I would presume that it will not worth much, let's say, because things are changing if it doesn't has all of these autonomous driving kits that is in there. And yeah, and then what we learned from this, that the project, the objective of the project is to study the effect of, let's say, different weather conditions on the performance of the LiDAR. And we've seen that fog is really the main effect. It has a major, let's say, effect on the performance of the LiDARs, meaning that there should be something that is needed to take care of this, meaning that, yes, there is an influence of let's say, fog, and then followed by the rain. The project, as I said, it is like continuing now, and we're continuing now we just started like a new phase of this project, and that would be running for another 2 years. And the focus of that project would be on looking at the like dynamic driving. That is one of the things, instead of like stopping, meaning that we go to the real thing where everything is moving around you. Some of the things are fixed, but mainly we want to look into the moving things. We're gonna look at the smog also effect. We gotta look at the tunnel effect, meaning that driving within in a tunnel. We're gonna look into a different situation where we have like dust also. That's another thing, that we go into some places where they have like lots of dust. As I said, smog. This is the conditions that we want to really study them, and those things would be also. We are the only one. Only. I mean, there were like some studies that's been done on like effect of rain. Fog was not there. Snow was not there, but also they were like mainly in the lab. So what we did here is just like we use it, like as we said, because Frostburg here has all conditions that's possible. It snows like maybe 10 times. It rains like every week almost. Heavy rain every two weeks. So we did instead of like simulating this in a lab, we said we'll use the actual real conditions that possible, and then we were hopefully we were successful in doing this. That is my talk, and I thank you very much for listening. And if you have, please